What up, peeps? We are starting to talk about magnetism, something you probably already have in your house, don't even realize. Of course, we have magnets on our fridges, right? But do you know where else you have them in all your speakers? Some of you might have electric can openers. Maybe you have some door latches that are on cabinets that have magnets. So let's start with the basic. What makes a magnet a magnet? Well, inside certain materials, because we know not everything is magnetic, there are tiny areas called domains. And they act like very tiny magnets, and it's due to electron motion within the atom. In a particular material that can be magnetized, your domains might look like this, where they go every which way. So like these are all little tiny magnets, if you will, inside the material. But it doesn't become a magnet until you get them to align. So how do we do that? How do you align domains? In order to align domains, you must have an outside magnetic field. You need something to make it magnetize. So how do we detect magnetic fields? We use these. This green on this compass is pointing north. I can line it up with north if that helps you. Remember, it's not about what's underneath. This goes to what we call magnetic north, which we're going to learn is not necessarily what you think it is. So I have a paper clip that I stretched out. And to see if something, so let me bring a magnet first of all. So if I bring a magnet nearby, you should see that this is a south pole. That green part, this little needle, a lot of people don't realize, is a magnet. That is the North Pole, and it is attracting to the South Pole. If I flip this around, the North Pole is going to attract to the silver, which is the South Pole. I take it away, it's going to go and point to the nearest or the strongest magnet, which is the North Pole, and it's pointing to the North Pole. I know it doesn't look North Pole to you because it's down, but in my room it is. So I have a piece of paper clip. I just stretched it out. And right now it's not magnetized. You can't see a whole lot going on. So the way to magnetize it, I'm going to take this out of the way for a second, is I literally take another magnet. This is my giant magnet, which I don't need to get near too many things. And I'm literally going to swipe it on here like 15 times. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is a really strong magnet. I'm going to get it out of the way. So I'm going to bring the compass back. And now you can see as I move this around, it's trying to follow it. It's not going to be a super magnet. When I put this side, it actually pushed away the green side, and it's now attracting the silver side. So this right here is the North Pole of my little paperclip magnet, and I'm going to flip it around, and the green is attracting. Again, it's not going to be super strong. I can bring it over here, and it will push the silver away. So in essence, that magnetic field took these domains in this paperclip and turned them into this, and now it will be magnetized actually forever. It'll take a long time to demagnetize. Okay, so what is saturation? Saturation is the point where domains are aligned as much as possible. You can only make a magnet so strong. There's only so much you can get. Now, there are permanent magnets. This is a permanent magnet. That paper clip is now a permanent magnet. Oh, look, see, it's sticking to there. The compass needle in here is a permanent magnet. So a permanent magnet simply keeps its polarity. It maintains its north and south poles. It doesn't switch. So what's a temporary magnet? Well, it will switch polarity and only in the presence, did I spell that right, of a magnet. All right, so little example. I have this metal ruler and I have this, it's a circle magnet. One end's north, one end's south. Actually, it's a bunch of magnets, but it's super strong. So I'm gonna take this end, there's a string on here, by the way. So the string at this end, and you can hear it, it sticks pretty good. You definitely know it's attached. That small section of this particular piece of metal, just like your refrigerator, is now becoming aligned temporarily to attract to this. If it were a permanent magnet, I would flip this over and it would repel, but it does not. It sticks. Just like if you have a fridge magnet that's just a bare magnet, you will usually be able to have it attract both sides. So right now, I just made the domains in this piece of metal flip back. That also can happen when I have a strong magnet and a weak magnet. Strong magnets can actually realign weak magnets just because they're stronger. But when I take this away, this doesn't have any magnetism. It only has it when it's in the presence of another. Temporary versus permanent. Okay, so we're gonna do some pictures real quick. We're going to draw the magnetic fields that you had with the iron filings, but we're gonna simplify them a little bit. All right, so first of all, we know that there's sort of a, what do you want to call it? A loop that goes around. I'm going to draw it bigger. Yours was a little bit more on the side, and we know we have some lines that stretch. But then there were some arrows, and the arrows are going to go on top the way the little compasses. Hopefully you remember those little compasses that we put next to it. So for example, if this is a north and a south, we are going to put little arrows based on how this north pole will point. So right here, it's going to point towards the south, but over here, it's going to point away from the north, and on the sides, it's going to point towards the south. So when we draw these lines and these arrows, it represents the way the north pole of a compass would point, they will always be directed towards the south. All right, so that's a simplified drawing, like maybe what it would look like on a test. All right, so the next one, I'm only gonna do the in-between spots. If I have opposites, we had that little bridge that happens, and it kind of curves. And we would put arrows to the south. Okay, when we have opposites, again, these are simplified pictures. Hopefully that looks a lot like when we had charges. Very simplified. So this is the north. They're always going to point away from the north. The picture here for the two souths will look similar, except the arrows will point towards the south. So in some ways, it's a little bit like electrostatics, where someone decided to talk about the way that a positive test charge would move. Here, it's the way that the compass would point, and we direct everything based on the way that the north would point, which is usually your color tip. But think about this. This is also a magnet, and its domains can get realigned. So generally, we always have to check our compasses, especially in my room. All right, let's go to the next page. So permeability is the ability of a material to concentrate the lines of force. One of the most common materials used for that is iron. So, and you would never put it between two opposite poles, first of all. So if you put them between north and south, so instead of having, I'm gonna just flash back for a second, this field, it's still gonna look like that, except that's gonna squeeze it down. In other words, I'm gonna use those same 5 lines. So let's say I have one here, one here, one here. So instead of being open, and then this one would come in really close. And again, the arrows are going to go towards the south, because that's the way a compass would point. it would take a normal field and concentrate it. And the closer the lines, the stronger, the absolute stronger the field will. This is done in motors, generators, all over the place. Okay, so here's some properties. The concentration of the lines of force is also considered its strength. Flux density, or the word flux. Flux refers to the strength of a magnetic field. They are directed north to south because we use the little compass, and that's how we use it. So if I say a compass placed in a field points tangent, I guess I could put a magnet here. It's going to point straight in. If I put it on the side, somewhere around there, it's going to point straight. So if I match that to these lines, it's going to fall right on these lines. It's going to point that way. So if I just do it singularly, I would have, if I had a compass here, it would point this way. If I have a compass here, it's going to go like this. It might be a little crooked, but if I put one over here, it's still going to point like this. But if I put one here, we know it's going to point away. And the combination of all these will make that field, which generates the magnetic field picture. Okay, magnets occur as dipoles, meaning two, no monopoles. So here's the thing. If I break a magnet, I'm going to go back to the domain picture for just a second. If I take a magnet and I break it down to the molecular level, I still have tiny atomic areas. So I will never just get one pole. I can break this and break this and break this, and all I get is smaller and smaller magnets. And of course, opposites attract, likes repel. Duh. You guys already knew that. All right, 3 kinds of magnetism. Ferromagnetism, that's the general, regular, that's what most magnets are made out of. Iron, nickel, cobalt, and any kind of alloy, like any steels that have them. There are some metals that are what they call weakly magnetic. Okay, manganese and cadmium, remember our chemistry here. And some things that are specifically just, they don't have the right electronic configuration and spins and movement to create domains, so they will not have a magnetic effect. Silver and copper are good ones, examples, and that's part of why they're used for money. Last but not least, well, what's the biggest magnet we've got? You got it, it's the Earth. So just so you know, there's something called magnetic north, and most people realize that on maps, we call this the North Pole. And we know that the magnetic north is a little off. Well, I'm not really worried about that so much. Why did I draw a bar magnet in here? Is that what's in the Earth? No. Inside we have the inner core, the outer core, we have the mantle out up to the crust. And inside the cores are where there's iron and nickel, and there's motion, and that's where our magnetic field is made. So it behaves as if there was a magnet here. And of course, every time we use a compass, okay, we know that it points to the North Pole, right? I can go here on the equator and it's going to point north. If I go over here, it's still going to point north. I go right up to the top, it's going to point north. Here's the problem. If I put a north here, north will never attract a north. The reality of magnetic north is that it doesn't actually exist the way you may think. It turns out that inside the Earth, at this point right now in our history, our magnetic north and our true north is actually really a magnetic south. It is not a North Pole. In the rocks in the bottom of the Atlantic Ocean, where magma has come through in the mid-Atlantic ridge, we have records to show that the north and south poles of our world have actually flipped over time, and that the North Pole was magnetic south at one point and magnetic north. So I know this is actually magnetic south. So let's label. First of all, we're going to put a south in here and a north. And the magnetic field around the Earth looks a lot like that of a bar magnet. The lines of force are stronger here. See how they're closer? And they're perpendicular. at the poles. At the equator, they are parallel and they're spread out. In reality, this magnetic field actually protects us from a lot of radiation from the sun. Sometimes radiation will come flying by the earth and come down into the North and South Pole, and that's where we get the auroras, aurora borealis, or if it's at the South Pole, aurora australis. So labeling this 90-degree latitude is considered geographic north, but at the same time, it is truly a magnetic south. And of course over here, just add it in here, of course this is geographic south, but it is at this time in history a magnetic north. Maybe that's a whole new world. All right, talk to you later. Peace.